Okay, before I start the digital simulation, I have stored this signal block diagram in a file which is called example 675 PID plus 2PT1 plus delay, and the signal block diagrams are stored with the suffix WLN. You will find these files and also the other files I produced here during videos in a folder in your course. Yeah. Now I close Windfc, we don't need it anymore. And I have already started the Windfc tool. Go to version 7.7.17 or higher. This program can simulate a hardware and run a real-time PID-T1 controller and many things more. You have seen this in another video, in the previous video, so I can now start the hardware simulator behind ADC cards. The hardware simulator has to be switched to 2 PT1s in our case. We have to change the parameters to our given values of the process. Gain 2, first time constant 0.275, second 0.165, no delay, sampling time you have to set to 55 milliseconds, and then don't forget, click on this button, because then this program calculates a digital filter which is working in the background as a simulator for our 2PT1 process. So these values are set. The algorithm here also must be selected, because this hardware simulator, of course, must work in synchronous way to our controller type, and here also the real algorithm must be selected, otherwise this doesn't fit. Okay, I close this hardware simulator. That is not closing, but making invisible, working in the background, still in the background. And I switch to the real-time functions. First point to the adaptive advanced controller. This is a rather large box with thousands of parameters. Later explained in more detail. We need only a few clicks to get our response of our 3 controllers. First, check the setting. The sampling time must be 55 milliseconds, fit to the hardware simulator. That's the reason why here the 55 is already available. We want to see not 100 points. We can decrease this to, I think, 50 points is okay. And we select first a PI block and a unit step function. Yeah, the presetting is 6 volt, 1 volt offset. That is presetting for a position control example in our lab. So click to unit step response. Then that is what we want to check. Yeah, the closed loop response of a desired step from 0 to 1. Here you can see the both queues of the controller, of the PI controller. We have done this before, but of course now we have to copy now our values into this box. Note, I have to check the values are 0.666 and negative 0.4555. Easy to keep in mind. So we go quickly back to this window and overwrite these values. Don't forget the minus sign, and don't forget to click on this button to send these values to the PID controller. Yeah, if you change other values, they were overwritten, but if I go back to PI controller, you see they are internally stored and can be accessed. Here is a real mode selected, that's what we want to show. And yeah, step auto stop. Step is going to desired value. You can also click on disturbance step responses. Starting initial conditions is no controller output. If I click on Run button, the initial conditions are valid. No problem here. All values are 0. No initialization has to be awaited. And I click on the reference step response button, and then we have to wait 55 steps after 50 milliseconds. And here you see, I give you a little bit better picture. Here you can see the reference step response from 0 to 2.5 seconds. You see there is overshoot, undershoot, little bit overshoot more than we expect with a phase margin of 60 degrees. This comes, we ignore, don't forget, we ignore the design, the delay time. But in the PI case, it is not so important, has not so big influence. So I see this curve is maybe acceptable. Now we have to switch to a PIDT1 design. We go back to the parameter box, and now we have to overwrite these 3 values with our PID values. I show you what happens. So I have to open the values 10.666 10.666 negative C16888 16.888 and finally 6.666. It was the PID design with ignoring the delay time. And now look what's happened. If I click on run button, we have to wait until this is 0. Note now this is a process output. If I start this, you see in the numbers you can see oscillations. This control loop, ignoring the delay time block, is unstable and starts an oscillation. So you have no control about the output. This control loop doesn't work. So ignoring delay time block could cause to very bad behavior. So I delete the last curve. Delete button, here you delete all curves. With this button you can delete the last curve because you of course want to have good behavior. We can auto scale the curve to the last situation and can now show you the third design. So I overwrite 2.844 negative 4503 negative 4.503 and finally 1.778 1.778. Okay, send these values to the controller, run it, wait for 0, start, and here you can see settling to desired value 1. The controller output, not the controller, but the process output is now controlled very quickly to the desired value 1. So you see after some steps, here is 0.2 seconds, 0.4 seconds after some step. After 0.4 seconds, you reach the final value with a small undershoot here. So this is a nearly very good behavior. I want to show you a last experiment, very short, quick experiment. What happens in our system if your parameter is changed a little bit? I change the parameter Q1 from negative 4.5 to negative 4.7. So this is small maybe typing error or unsafe copying the values, anything else, I type in a 7 here. Send this value to the loop, activate the controller, wait for initial condition 0, and note what happens here with the controller, with the process output after I start the reference step response. You see a dramatical change of the output. A very small change of the second digit leads not to a stable red curve, but to an unstable green curve. You lose the control over your system. The system starts in going to big negative values, exponentially crash down. Yeah, so be careful with the accuracy of your Q values that are very important. If you change the K or T values, there is a good tolerance, 10% doesn't matter, but the Q values must be very accurately typed in. Okay, so far I close here with this experiment, chapter 6. You can find these curves also in the paper as a screenshot. Bye bye. Next video starts with chapter 7.